Hello and welcome to this lecture on the base matrices in the 5G new radio standard. Okay. Like I mentioned, the 5G standard specifies parity check matrices for LDPC codes using this base matrix and expansion method, except that there are two base matrices and several possible expansions. Okay. And the base matrix itself is quite large. It's not a very small base matrix. In my example, I showed you a 3 by 6 base matrix. The base matrices in the 5G standard, there are two of them. One is 46 by 68, the other is 42 by 52. Okay, so it's quite a large base matrix. Okay, 46 by 68 and 42 by 52. Okay, quite large. Okay, and the base matrices have a very useful structure. Okay, so even though they are large, so it turns out you can carve out some small matrices from them, and these matrices have a very easy structure. So in particular, there is a block structure. Okay, so they have a block structure like this. Okay, the first block is A, first row block is A, E and O, and the second row block is B, C and I. Okay, so in the base matrix the first base matrix BG1, A is a 4 by 22 matrix, E is a 4 by 4 matrix, O is a 4 by 42 all 0 matrix. So when I say all 0, I should be careful here. So it is actually all minus ones, remember. Okay, so in the base matrix it's all minus 1, so it gets replaced by, when you expand, it gets replaced by the all 0 matrix. Okay, so B is 42 by 22, it's much larger, right? So 42 by 22, C is 42 by 4. Okay, and the I part is actually an identity. 42 by 42, it will have an identity structure. Okay, so I'll show you some examples later on. Okay, so this block picture is very important. The first row block usually is dealt with separately in the encoding part, and the second part is dealt with separately. Okay, so it's important to know this block difference. BG2 also has a very similar structure. Okay, so remember BG1 is 46 by 68. So you can see 4 plus 42 is 46, and then 22 plus 4 plus 42 is 68. Okay, and the base graph 2 also has a very similar block structure. A 4 by 10, 4 by 4 and 4 by 38, and then B is 38 by 10, 38 by 4, 38 by 38. Okay, so easy enough to describe. The standard goes into details on what these each of these things are. I will show you some pictures next to illustrate how this looks. Okay, so how does the block look? This is how it looks. This is my A part. Okay, this is BG2, by the way. This is E, this is O. Okay, so you can see O is like the empty part. So this is okay, I should tell you how I got this picture first. So this is a visualization of the base matrix. What I've done here is minus 1 is ignored. Okay, if the base matrix entry is minus 1, I've just put space there. Okay, I'm not showing it because it gets replaced by all 0. Okay, 0 to any other value, 0, 1, etc. Right, I'm showing as a dot. Okay, the blue dot. That's the visualization, just to show you how the structure looks where the non-zero values are. So you see this A part is fairly dense. Okay, a lot of non-zero values. E also has a very peculiar special structure. It's called the double diagonal structure. Okay, you can see if you come in and see closely, you'll see E has one main diagonal and an off diagonal. Right, so you can see the main diagonal and the off diagonal. This is the double diagonal structure in E. This is all 0. So there's nothing in this. I mean, all minus ones, all zeros. Okay, and then you have the B part, which is this big part, and then what did I call this? C, which is this long rectangular small part, and this is the identity part. And you can see this is just diagonal, and in fact all these entries are zeros. Okay, as in they are replaced by an identity. So overall, even after expansion, this will be identity. Okay, this will be all 0 after expansion. Okay, the top O part will be all 0. So this is how the matrix will blow up. Okay, so even though, like I said, this is a pretty big matrix, it's 42 by 52, you can sort of stop here if you like. For instance, you can do this. Okay, So this small part is another base matrix. You can ignore all these other things, you can sort of puncture all these things out, you don't have to evaluate those parities, only use this part of the base matrix to transmit your code word. Okay, you can do that, that sort of thing is called rate matching. So you can choose to do that. In fact, the first two message blocks are not transmitted at all in 5G. Okay, they are always punctured. These two guys are always punctured. Okay, so I don't want to spend too much time on the rate matching and all these things that happen in 5G. I want to focus on the LDPC decoder first, and then maybe in a later lecture I'll point out how the rate matching actually works. So even though this whole parity check matrix is very big, you can see this large identity part allows you to just cut off wherever you like. Okay, so you can get smaller base matrices and different rates quite easily from this matrix. Okay, so like I mentioned, I'm not going to spend too much time on thinking about rate matching in these lectures, but it's good to know where they come from. Okay, so this is how the matrix looks. The entries themselves are very different. I'll show you some of the entries in a few examples in the later slides. Okay, so hopefully this is clear. If you go to the standard document, there will be a clear description of how to construct these base matrices also. Okay. Okay, so now what about the expansion? Okay, now the expansion, the base matrix I told you has size 42 by 52, 46 by 68. Okay, that is the base matrix size. Okay, now there's something called index, which is ILS in the standard. It's just a way to order the expansions. And then there are two factors here which control the expansion. There is a factor called A, and then there's a factor called JA, and the expansion is A into 2 power J for J going from 0 to J. So there are a lot of expansions possible. So if you look at A equals 2, it corresponds to expansion of 2, 4, 8, 16, right, all the way up to 256, right. So 32, 64, 128, 256, right. So this is this corresponds to J equals 0, this is J equals 1, all the way up to J equals 7. Okay, so those are all the expansions possible, and you can figure out where the largest will come from. It turns out the largest expansion is 384. Okay, so this is just given to sort out all the expansions. Now for every base matrix and for every expansion, there has to be you have to fix the values. Okay, you have to specify what the values are. Okay, so for each ZC, the base matrix values are specified. They take values from -1 to ZC -1. Okay. All right, so let me repeat this once again. For each expansion factor defined in this fashion, there are a lot of expansion factors like I mentioned. For every A, you have to multiply with 2 power J, J going from a certain range, and so you have a lot of expansion factors, and for every expansion factor you have to specify, the standard clearly specifies what the base matrix entries are. Okay, so you have to look at the standard document and figure out what the base matrix entries are for each expansion factor. So in short, given a base matrix and given a base matrix and given an expansion factor, you can find out the exact entries in the base matrix from the standard description. Okay, so that is something you can write a program for if you like. It's possible. Okay, so I'm not going into the details of how that specification happens in the standard. I will encourage you to read it on the standard document. I'll provide a link for that as part of the course material. You can go look up the definition. There's a lot of detail there. We will skip that, but I will provide the base matrices themselves for every possible base matrix, base graph 1 or 2, and the expansion factor. I will give you the base matrices directly, so you don't have to do that. But nevertheless, it's good to go look at the description and figure out how the base matrices are specified in the standard. Okay. Okay. So here's an example of a base matrix. So I've not shown the entire base matrix here. The BG2, if you remember, is 42 by 52. I'm only showing 10 rows and 20 columns. Okay. So after this, below this and to the right of this, there are a lot more entries in the base matrix. I'm skipping all that. This corresponds to ILS equals 3, J equals 4, and ZC equals 48. So this will correspond to some A value. I believe it's 3. Okay, so I think this is A equals 3, right? So 3 into 2 power 4 is 48. Okay, so this is how the entry looks. So ZC is 48. So the base matrix entries will go from -1, 0 all the way up to 47. Okay, so you can see there's a 47 here, there's 26, 36, 46, all sorts of entries here, and so what I've shown here is the E part, the matrix E, and this will be the O part, this will be the A part and all that. I'm drawing some special attention to E here, I'll tell you why. And then you can see the identity part coming here, right? So this is the identity part. Okay, so you can see the 0 along the main diagonal and then -1s throughout. Remember, 0 gets replaced by the identity matrix. So overall, after expansion, you will get an identity matrix here. This O will be a big 0 here. Okay, and then these entries are all over the place. Okay, so I mentioned this double diagonal structure in E's, right? So this is diagonal, everything else is 0, and then this also has a peculiar sort of form. Okay, so you will have this 1, -1, 0, 1. So this plays an important role later on. We'll see that in the encoding, it will play a role. Okay, so we'll come to that when we see it. Okay, so so this is how it looks, right? I mean, there's nothing much more to talk about here. So these things are specified precisely in the standard, and like I said, we are not going to see the full description, but this is how the matrix looks. For any other case, the entries are specified. You can go find them and write it out and look at it very closely. You will get numbers like this. The only part is this E part. I will urge you to look at the E part and everything, and this first column will also have a peculiar structure. So later on, I will talk about why this is true, why this is useful, this double diagonal structure. So this is sort of useful in encoding. Okay, so this structure is useful in encoding, this double diagonal structure. I'll mention that later on in a lecture. Okay, so this is one example. I think this is the last slide. What I want to do is show you. So I promised that I will show you the base matrices themselves. So here is a folder where I've written a program to generate all the base matrices in the NR standard. So you can do that, and then this is just written down here for every single possible J and ILS, and then I'm just going to show you some of the base matrices that are there. So you can pick anything else. So for instance, let's say we pick this one. Okay, so it's a rather large base matrix. Maybe I can blow it up a little bit. Not sure how visible this is. Okay, so like I mentioned, I've written a program to look at the standard and then pull out all the base matrices, and so this is all the base matrices as text documents. So let's pick out one such base matrix. This has got an expansion factor of 208, and you can see how the matrix looks. So this is the base graph 2, once again 42 by 52, and you can see the dense part here with A, B and C, and the E part here, right, and then the long identity part here, and then the all zero part here. Okay, so this is how the base matrices look, and you could write this as well, but I'm not sure if for this class it's so crucial for you to write the piece of code for generating these base matrices. So what I would do to help you out is to provide the base matrices themselves. So I'll create a Google Drive folder and share it on the course page. You will get access to all these files, and you can look at the base matrices and pull out the base matrix for any particular specification. Like I said, it's not a big secret. It's there in the standard, except that you have to read through and write a small piece of program to create the base matrices. I'm helping you out there with providing the base matrices myself. Okay, so the main focus of this course is on building decoders for these codes. Okay, so like I said, how do you make a decoder? How do you describe and write down code, MATLAB code for a decoder for these kind of parity check matrices? Like I said, this is just specification of the parity check matrix. From here, how do you build a decoder? Okay, so that's going to be the main challenge as far as this course is concerned, and let's focus on that mostly. Okay, so instead of worrying about how to create the base matrices. Okay, so this brings me to the end of this lecture. From the next lecture onwards, we'll start looking at decoders for LDPC codes. Okay, thank you very much.